Good, good. So, I will have one or two of these for you to do, but I want to go through the whole process of sketching a nonlinear phase portrait. I'm also going to ask you to do some numerical stuff with the app that we use. I'll show you what I mean today. I want to introduce a new version of the Lotka-Volterra models, and then show you what I'm going to ask you to do. I'm going to ask you to do actually a couple of things, but let's go back. So we have another Lotka-Volterra. These are the very first simulations of biological systems ever created. And I don't honestly know much about Lotka or Volterra, except that they kind of set the standard for these. These models are not truly accurate. You would never be, if you're a biologist, wait, or do we have biologists in here at all? No, okay. Yeah, if you were a biologist, you would not use this at all to model some sort of policy you were trying to work up, or any sort of actual study, but they can be tweaked to be more accurate, and they do give realistic-ish results. So let's look at a new one here. The last one we looked at was a competing species. This one is a predator-prey model. Competing species. So what we're going to look at today are, instead of sheep and rabbits, we're going to look at sheep and wolves today. And you could make these letters S and R if you wanted. So these are Greek letters. That's an alpha, beta, delta, gamma. And I've got some specific values for us, but I want to talk about why this model makes sense to us first. So the first thing is the X is the prey. So X at T equals the population of, let's just say, wolves, but really it's the predator in this system. And then Y at T, at time T. And then Y at T is the population of rabbits, the prey. At time T, blah, blah, blah. Yay! I knew you were lost in the eclipse, so.
I was hoping Jordy and...
I appreciate all your eclipse love and helping them out. So let's take a look at this model, and let me see these XY terms? Those are the interactions between the two species. Let's just assume for a second that beta was 0 and delta was 0. So in the case beta 0 and delta 0, there's no interaction. So we could imagine this X dot model looks like this, and the Y dot model looks like this. And these are things that we could solve right off the top of our head. In fact, we can write out the solutions for this one. This would be X at T is some constant times e to the alpha t. And this one is Y of T equals C e to the negative delta t. Yeah, and I would say another thing here, alpha, beta, gamma, delta, these all positive. So this one says that the predators are going to grow unchecked. Wait, is that, yeah? What?
If there's no interaction, why are the rabbits dying off?
Yeah, that's what I was actually wondering myself.
At first you said that X is
yes.
Supposed to be rabbits, prey, and then you changed it to predator.
Oh shit, I got it backwards. Yes, thanks. I got it backwards. Yeah, thank you. So this should be X of T is
prey.
Prey. Thank you. Got my words backwards. So this is the population of rabbits, and they will keep growing. Thanks for catching that. Nice catch. So that is the prey, and this is the wolves. Yeah, good catch, Mike. Those are the predators. So the thing that cued going off to that was that here we have growth, pure exponential growth if alpha is positive, and we would expect that to be the population of rabbits just growing, eating grass happily, just ever reproducing and becoming more, whereas the wolves in the absence of rabbits have no food and they would die off. So for this one here, we have exponential growth. So rabbits grow population-wise in absence of wolves. And then here, the wolves die off in absence of rabbits. And we are just assuming the rabbits have some kind of food supply that just keeps them going. Cool. But then there's interaction. So let's look at this interaction term. First for the rabbits. So again, unchecked growth in the absence of wolves. But when there are wolves, the population of rabbits times the population of wolves gives us a measure of the interaction. If either one of those goes up, that quantity goes up. So this is somehow simply modeling interaction between the two. And since beta is positive, the more interaction there is, the slower the growth rate of the rabbits. So this is the term that says rabbits are getting eaten by wolves. And the more wolves, the more rabbits get eaten. And the more rabbits there are, the faster they can be eaten. Similarly down here, the wolves are going to die off without the presence of rabbits. But as soon as we have rabbits, the number of wolves times the number of rabbits gives us a measure of the amount of interaction they can have. And we see that since delta is positive, this y dot gets some positivity added to it. So this would increase the growth rate while this is fighting against it. So look at the tension here. Growth, death, growth, death, and how do these things balance out here? So this is the model I'd like to sketch. And we're going to see something weird, and we're going to get a computer out to verify our suspicions. So step one, let's, sketch a face portrait. I'm going to ask you to do this by hand. Classify all equilibria and connect into a reasonable portrait. When I say connect, I mean the equilibria. So step one is linearize, but I'm actually gonna make some numbers here. I don't really feel like carrying around alpha, beta, gamma, delta. You probably don't feel like hearing me say that over and over again. So let's say that alpha is 2/3, beta is 4/3, gamma is 1, and delta is 1. So actually, the system that we're looking at looks like this. Sorry, I'm a little jumbled from the eclipse excitement. There we go. Step one, find the equilibria. Step one, and then step two is going to be linearize this system and find the Jacobian, but step one can sometimes be hard. So find equilibria. And along the way, we're actually going to find the curves for the nullclines as we do this. And I'll point that out. That's something I didn't really mention last time, but it'll help your portrait. So we're going to set x dot equal to 0, y dot equal to 0, and figure out where that happens simultaneously. All the x, y pairs that make this true. So for this first one, we got 2/3 x minus 4/3 xy equals 0. And then for the second one, we've got xy minus y equals 0. Any suggestions on where to begin? Let's actually sketch out this and sketch out this before I take your suggestions. So notice that this one here, this is the null climbs. This is where there's no horizontal change, pure vertical change. So we've got 2/3 x minus 4/3 xy equals 0. How would you figure out where that's happening? What could we do there? Just looking at this, not thinking about the problem. If I said solve for xy, what would you do? Lulu, what you got?
Factor it.
Factor it, yeah. There's some nice factoring that happens here, right? We've got a 2/3 x that can come out front, and then I've got 1 minus 2y, and that's pretty lovely. So this tells me that when x is 0, or when y equals 1/2, x dot is 0. Let's do a little sketch in the middle and do our summary here, because this is all the general setup. And if you don't understand something I'm saying along the way, please let me know. And actually, since these are populations, we don't really need anything but the first quadrant. We just assume these things are non-negative. It makes sense. All right, so x equals 0. So this is x equals 0 or y equals 1/2. If x equals 0, I'm on the y-axis. And notice that there, I've got no horizontal change, so I've got either pure up or pure down. But right here, I've got, you can check this out, what is the value of y dot on this line? It is positive. And then I've got y equals 1/2, so let's say there's 1/2. And all along that line, I've got pure vertical growth as well. And we'll check the direction in a minute. Let me stop and tell me if that's making sense. Yes, so far I'm seeing some nods. Yeah. So this is, let's make a little note to help keep our brain together. Otherwise, I might get fried as well. Let's see here. So we've got, this is where x dot equals 0, right on that axis. Okay, so what about the other equation? So I'm going to take Lou's suggestion for this one and factor. If I've got xy minus y equals 0, you might be tempted to do this. I was thinking somebody's going to want to do that. And then they're going to cancel the y's. That's totally legit as long as y is not 0. But realize that y equals 0 is also a solution. So you can either do it this way and say y is not 0 so I can cancel it, or y equals 0 and it's true. But factoring is the more kind of complete picture. Then I see that x equals 1 or y equals 0. And this is where we have y dot is 0, so this is pure horizontal growth along these curves. So, all right, so when x equals 1, let's see if that's 1/2, and x equals 1 maybe is about right there. I've got that, and I've got pure horizontal change along that line. That's x equals 1, and then at y equals 0, that's my x-axis. So all along here, I also see growth. And now I should check. Let's see. We can actually use some of this stuff here. The x dot is going to be positive because this is our rabbit population. So in the absence of wolves, we already talked about how that would grow. And that actually means this must be negative because this is where there's only wolves. And they die out if they don't have any rabbits. So that must be a negative flow that moves right there. Does that sound reasonable? Let me know if anything's not clear. Happy to help figure it all out. So rabbit keeps growing, no wolves. Wolves die out, no rabbits. That's going to help us out. And then we've got all our lines. We can figure out the flow in a bit. We'll just take a few samples in there to see what those arrows are actually doing.
Wait,
Yes.
so X line is rabbit, right? And then Y.
X line is the rabbits,
Y
yeah.
line is wolf.
Mm-hmm.
So as the rabbit keeps growing, so do the wolves grow, right?
Well, we haven't moved up into there. This is just this is where there's no wolves on this line here, Lou.
Oh, okay.
Does that make sense? And this is where there's no rabbits on this line only.
Okay.
And when there's no rabbits, there's no food, so the wolves die out. Yeah?
Yes.
Okay, cool. Awesome. Step 1 is find the equilibria. Wherever these things intersect are equilibria. So in other words, I've got 4 different equilibria here. And you can just take all the pairs. Notice that we had x equals 0 or y equals 1/2. And then also x equals 1 or y equals 0. You just got to keep your head clear on that because this is going to give you 4 different pairs. First one's going to be 0, 1. Well, let's just go 0, 0. And then 0, 1. So here I'm just using x is 0 for both those, taking both these possibilities. Not really, am I? Hold on, buddy. So, okay, got it to slow down. X is 0 or y is 0, so there's just that guy. These two don't mesh because they're the same information. This is x info, this is x info. I'm going to get, I guess I'm only getting 2 equilibria? Is that right?
Because there's one half.
Oh, I need to go this way too. Well, let's see here. Yeah, I kind of need to get all the 4 pairs, yeah. So we've got x is 0 or y is 0. We've got x is 1 or y is 1/2. We've got, no, I think that's it. No?
You
What
can
am I
do X of
missing?
1 and Y is 0,
Zero.
right?
No,
Say it again.
because it won't solve.
So we've got this, so let's check this out. So this is the x dot equals 0. So I want one of those 2, but I also want one of these 2 where y dot is equal to 0. So one of these 2 makes x dot 0. There's only 2 places where that happens. And then this one makes y dot 0, but we can't say x and x because this is, we can only do xy pairs here. So I think there's only 2.
You can't do 1, 0? Is that because that's or?
So you're saying
X1,
1, 0, is that Cormick?
Yeah.
Yeah, so I can do this x is 1, but this is still x is 0, not y is 0. And, oh, I guess, well, no, we can't, Cormick, because if x is 1 and y is 0, that doesn't make this 0. I want both these things to be 0 simultaneously, so it's true that if I use the point 1, 0, this thing is 0, but this guy isn't 0.
Yeah.
It's a little confusing. Does that help?
Yeah.
Okay, cool. Thank you for asking that. That's a great question. So we really only have 2 equilibria, and they are at the origin, and they are at this crossing right here. And that's good news, because that means we only have 2 things to classify. So step 2 is find the Jacobian. And the Jacobian is this matrix that is, let's see, let me get a little notation. If I have x dot is that equation and y dot is that equation, the Jacobian is first partial of f with respect to x, first partial of f with respect to y, and then first partial of g with respect to x, first partial of g with respect to y. Notice how they're lined up. The x dot stuff is on the top row, the y dot stuff is on the bottom row. First column is with respect to x, second column is with respect to y. So could you take a minute and find those for me? What is the Jacobian? And we find it first in its generality, and then we'll plug in our equilibria. Just to practice this. If it's been a while or it's been never that you've done this, it could be. And I'll put these up here and you can check yourself. Yeah, I think that sounds good. Let's make sure we're all, that's grooving for us all. Did I get it right? Anybody else get it? Seen one nod, that's cool. So, me and Tara are voting yes, that is correct. What is anybody else voting? I feel pretty good about the first row. Now I'm feeling pretty good about the bottom row as well. Does this need any explanation? No. Good. Gonna have to do this. It's gonna look very similar when you do it. That's step 2. I don't know if I made the next thing a step 3 or not, but part of this is now plug each equilibria into J of XY, and what you're gonna get is essentially a linearization of the system. We're getting an approximation for the system at that equilibria. So when we do that at J of, you gotta make sure I only use my equilibria, 0, 0, the matrix is gonna be 2/3, 0, 0, -1. What are the eigenvalues?
2/3 -1.
2/3 and -1, awesome. I was just in linear algebra class last week. I saw you guys starting on this stuff. And I was hoping my DiffEQ students would be able to just read those suckers right off there. So does everybody see how I'm getting that lambda is 2/3 and -1? I don't even need to go to the delta tau plane. What is the behavior at 0, 0? We've got those basic portraits. What happens at 0, 0? Is it a source, a sink, a spiral? Saddle. I've got outgoing and incoming. These are the velocity vectors on the eigendirections. So this is outgoing, this is a source, and this is a sink. And together, that gives me a saddle. And it kind of makes sense with what we already kind of grokked from just thinking about the populations alone. Here at 0, 0, I've got sourcing along the rabbit direction because rabbits grow when there's no wolves. And I've got sinking along this direction, so I really actually have the eigendirections as well. So right here, let's just make a little note. That's a saddle. Cool. Makes sense with what we have. Tell me if that needs extra explanation. I'm super happy to talk about it. I'm gonna clean up over here. We've got one more equilibria to evaluate, and it's this critter in the center. We're gonna see something really neat here. Maybe not unpredicted either. Something we could have guessed. So J at, I'm gonna assume, let me take a look at y'all. Does that sound okay? Okay, could you do this one, please? I'll just let you do it. What happens at this equilibrium in the center of the plane? Find the Jacobian, you've already got the general formula, classify, see if it makes sense to you. And once you have this, I think we're gonna be able to fill in a lot of details. Let me get the computer model. See, and once you get that, see if you can fill in what happens. If you're gonna get a prediction that I said you gotta be wary of it, but I'm gonna say trust what you find and go with it. This is a shaky possible prediction, but here it turns out to be completely legitimate. X is 1, y is a half. So I've got 2/3 minus 4/3 times a half. That's gonna be 0, but I'm gonna write out the scratch work here. Negative 4/3 times 1. Lower left pocket is gonna be a half. And then I've got 1 minus 1, so I've got a 0 here. Did I do that all okay?
Yep.
Cool. Cool. You're in agreement with me, Lou? Awesome. So let's simplify. That's actually 0, negative 4/3, 1/2, 0. Can't read the eigenvalue. That's not a diagonal matrix, so don't get fooled by that. The diagonal has to be down and to the right. What do we have here? What y'all thinking? Center, definitely. Let's do the classification. Tau is equal to 2/3, it's positive. Trace is 0. If the trace is 0 and I have a positive determinant, I'm on this axis right here. This is where the centers live. So I know I have a rotation around that point. And look at all the arrows. I can now kind of just pull this all together, making it consistent. Which way is this gonna rotate, clockwise or counterclockwise? Counterclockwise, because it's gotta be consistent with this stuff. This is almost creating a current as we flow around. So here in the center, our map, and look, I've got these isoclines, those have to be the tangents. Doesn't that look so pretty? As I cross each one of those, got a horizontal or a vertical tangent, like so. And just like Lou told us, we've got this. And we basically have just a whole bunch of these. The whole plane is filled with these things, and they become a little more irregular as we get closer to the axes, but we have circulation. Does this make sense? Somebody want to tell a story about just one of these? It's not a love story. Let's say I had this initial condition right here. And it looks like, well, I'll tell the story. How about that? What does that look like? Maybe let's say there's like 3 halves. So if my initial condition is y is 3 halves, x is 1, that means I've got, let's say, 1,000 rabbits. And I've also got 1,500 wolves. So what happens? Well, the wolves, there's a lot of wolves. They start eating the rabbits, so the x-coordinate diminishes. The wolves are eating the rabbits. And then there's fewer and fewer rabbits, so the wolves actually start to die off as they compete for food. At this point, there are the fewest wolves that the system, right here, that the system sustains. And because there's a dearth of wolves, there's more food for them to eat, so they start actually coming, oh wait, what do they do? No, they're still dying out, aren't they? Yeah, wolves are still dying out. What is happening right here in terms of wolves and rabbits?
There's the same amount.
Yeah, kind of, almost, right? Kind of, if that was right on that diagonal. Yeah, but here we have the minimum rabbit population. So that's the min rabbits that we'll see. This is the max wolves we'll see. I think this is what I'm trying to get at. And then once we have min rabbits, and there's fewer wolves, what happens? Wolves keep eating the rabbits, so we've got wolves dying off still. Wolves are still dying off. Rabbits are starting to come back. What about right here? This is min wolves. It's not our max rabbits yet, but I guess that once there's min wolves, and I guess as the wolves decrease, the rabbits have a chance to come back. And then like right out here, what we've got max rabbits out here. If we were to take a look at these as separate charts, I was trying to find an app that would do this for us. If we,
The graphing app that you gave us can do that.
can it? Can it actually do the separate?
Yeah, you can do a time plot. And it's
Oh, look at that. That's what I was hoping. You're gonna have to show me. I couldn't find it in my spastic few moments this morning. Let's take a look at this. Let's actually get this. So I'm going to the Bluffington app. That doesn't even look like it's on, does it? Now I hear stuff. Let's pop the system in. And I'm gonna want you to actually do this as well, my friends, so. If you've got your laptop, you might wanna play along. But if not, I'm gonna show it what's going on here. So we have got, thank you, sir. Awesome. So we got 2/3 x minus 4/3. Oh, I don't have, do I have the system? Yep. Okay. 4/3 xy. And my other system is going to be just xy minus y. Thank you. How did you get these?
You got it for the little multiplication sign.
Oh, does it need those? Is it gonna barf without them?
Okay.
Okay.
I think it's.
Thank you. I think you're absolutely right. That's what's unhappy. Okay, cool. That looks very happy.
And then you gotta press one of the points in the quadrant one.
Okay, yeah, let's max this out. So over here we can change our view, so let's make it 0 as a minimum. And then, see, now we're in lovely, just first quadrant. I'm gonna keep it like that. I think I'm gonna zoom out a little more and give us a little more space. So let's go to 6 here and then 6 here. And there's square window. Cool. So, how did you do?
You see these where it says table, next to it there's time plot.
Yeah, got it. Awesome. Thank you. That is beautiful.
And if you zoom out on that, you'll see like more of the little curves.
If you zoom out
And
on
then there's like up here there's like a negative sign,
Uh-huh.
so you can zoom out.
Oh yeah.
Bunch of times.
Oh, that's fantastic. Thank you.
Yeah.
So the blue is the population of wolves and the X is the population of rabbits. And it's a lot more complicated than just one's at its max while another's at its min, but we can see these here. And I don't think it's as easy to see right there. And also notice that the shape I drew is like not at all like the actual shape. I drew circles. This is a really strange shape for the actual population growth. So if I were to ask you to study a particular initial condition and what happens. So in fact, let's say I do the one I was saying where we had 1,000 rabbits and 1,500 wolves. So I'm going to set my initial condition to 1, 1.5. And then I'm going to hit submit. And there we go. Now I actually have the precise information. And we can see how they ebb and flow together. Oh, look at this. Wow, that's cool. Look how it moves along the thing at the same time. It's freaking awesome. Thanks, Wayne. I knew I had seen this at one point in the future, or one point in the past. I don't even know if I'm in the future or the past right now. So, and then if you want real table data, you can come over here, and this gives you the numeric information. Now, let's talk really quickly about this little drop down, and then I'll let you go. I'll have an assignment up tomorrow morning for y'all. You probably want to go with Runge-Kutta method, especially RK4. This is the only one we've really done much work with. We did a little improved Euler, but look at how bad this is if I use Euler. So let's just take a look. I'm going to clear these out again. Clear the curves. Look at what happens if I use a poor numeric method. Come on, bro. See how it's spiraling? That's actually faulty information. So the best thing to do here is to go to the best method you can have, probably this RK45, honestly. Look how it cleans it up all instantly. And you get those nice orbits. But this is an illustration of the thing I was talking about, that when we predict centers, we have to be really careful because centers are easy to screw up, like that. So if your numerical method is poor, you might think it's not a center. You really need to have high precision. But more importantly, let me tell you how you could prove this if you didn't have a computer with you. Let me show you the basic kind of argument that one could use. And then I'll let you go. What you can do to prove that this isn't an outward spiral, at least, is you can mark off a little region around the equilibrium, and you find certain spots where all the inflow is I'm going to take that back. So there's a theorem called the Poincaré-Bendixson theorem that I really need to look up the exact statement of, but it's a way to prove to someone that you have a center and not a spiral. But I need to get the deets on that, and I'll make a little video and post that for y'all. Anyway, what I'm gonna want you all to do is one model like this, rabbits and wolves, gonna be pretty much the same thing. The centers will be different, the equilibrium will be a little different. And then one other model that's gonna have two spirals in it. And that's pretty cool. And then like a saddle. So I'll give you all the information. Let's talk about class for the rest of the semester. Sorry I'm so spazzy today. It's the eclipse. I'm just gonna blame it on the eclipse. So we meet, let's talk about, let's see, Wednesday this week, and then Monday, and Wednesday of next week, and then Monday and Wednesday, and then we have our final on the Monday of finals week. If we have an in-class final, I'm still not 100% convinced that's going to happen. I would like to give you some face portraits and stuff to sketch, and this stuff takes time, right? You can't just come in and do this quickly, nothing meaningful. So I'm going to start, we're going to go back to one-dimensional systems, and we're going to talk about higher order systems starting on Wednesday. Higher order ordinary differential equations, not even systems. So this is things that have second derivatives in them, third derivatives. It's actually a pretty simple step up from where we've come. And then Monday and next week, we're going to continue that. Next Wednesday is going to be outdoor class, and we're not even really officially meeting. It's math on the quad. I will give you an assignment. I will want you to come draw something and tap me on the shoulder. Just have me look at it. I'll give you a thumbs up no matter how good or bad it looks. I just want chalk on the sidewalk. And then I think we'll just continue this stuff here. It's possible that this Wednesday, I'm actually starting to think this is more and more possible. We'll just have a work day. And that might be the day that I hand out the final, and then we just start on it in class. And then for the final, if we have a take-home final, I'll just have office hours during our final time that we can get together and meet. I think we're gonna have a take-home final. Does this sound okay? I think it's happened. It's like all of a sudden just resolving for me right now. So there we go, Tracy. We got it worked out. Cool, friends. Thank you everyone for showing up late and being here and dealing with your spaz prof. I appreciate it. It's gonna get worse in just a minute. About 15 minutes. Good stuff. What's up? Hold on, let me stop this recording.